Okay. Hello, everybody. It's kind of hard to go after a student. I always think that the dull, boring old NASA guy is now up instead of the exciting student. Anyway, what I'm going to do today is talk a little bit about the technologies that we are, in fact, investing in right now to get us to Mars with people on the surface. And so there's a bunch of technologies that are necessary. Those technologies form a very large gambit from the propulsion capability or transportation capabilities to get us there, to being able to live on the surface of Mars, to get down to the surface of Mars, and be able to get home. So we'll cover, if you looked at a lot of the things that were covered today in various talks, you saw bits of these technologies, capabilities that we actually need to get there. So let's see. If you think about the Space Technology Mission Directorate, that's its job. It's supposed to do everything that's necessary for the agency in terms of both getting people to Mars, supporting human exploration beyond low Earth orbit, supporting the Science Mission Directorate and its missions, and also supporting the overall aerospace industry in this country to raise the bar so that there are more capable missions from the commercial side as well as in the government side and NASA missions. So we do that through a pipeline of technologies. In other words, it isn't just the demos, the flight demos that have the highest level of profile or highest appeal or highest interest, but it's everything down to sponsoring university students to be the next generation as well. So we have people in the early stage area in our grants programs. We look at advanced concepts that are very far out there, way beyond what we'll probably live to see in terms of what happens next with space. We're doing the SBIR program. This is small businesses. And this is all at the lower TRL. This is where we're just coming up with the innovations, the next ideas 10, 20, 30 years out. In addition to that, the Space Technology Mission Directorate is covering the mid-TRL. These are the laptop experiments, the proof of concepts to see that that technology actually works. And finally, we're doing the large-scale demonstrations of proving that that technology can be turned into flight hardware and flown in space so that it could actually be infused, as we call it, onto future missions. So how do we do this in support of human exploration? And we actually look at the ISS as a test bed, as a demonstrator, as a place that we're actually developing technologies. That's one of our big tenets of supporting the Human Exploration Directorate. We're developing targeted technologies to advance the capabilities on both Orion and SLS. We're working with the Advanced Exploration Systems, which you'll hear about tomorrow from Jason Crusan, and the Space Communications Network group to develop next generation capabilities. And we're focused on specific technologies ourselves, specifically for Mars. Now, I'm not going to cover the ISS piece here today, and I'm going to go into some of the other technologies. In several of these charts, there are lists of technologies that we're investing in. I'm not going to cover those, but if anybody has any interest in any one of the technologies that's mentioned on any of these lists, please get a hold of us. We'd be happy to talk to you about it and provide you much more details on any of these technologies. Instead of doing this, these are specific technologies for Orion and SLS. I'm going to go into a little bit of detail on just a few of these examples. So one of the key things that we're working on is advanced thermal protection materials. Woven TPS is a new type of thermal protection material. It covers a wide range of capabilities. The first instance of it we're applying is actually going to be Orion compression pads. These are critical path for Orion. This is actually carrying the loads between Orion and the rest of the vehicle that launches it during ascent, and then once it's in its entry phase, it actually acts as a TPS material. So it's a dual-purpose material. It has to have very high density, but it also has to be compatible with the rest of the heat shield that is much lower density. And so in some sense, it's at this extreme end of the density spectrum, this high density. And you can see that the woven TPS materials actually allow you to go across this wide density regime where you have these traditional TPS materials laid out. So it reduces our TPS integration challenges because in one variant of the woven TPS, it is entirely compliant. If you think about TPS materials that we have used in the past, and that's including things like shuttle tiles, but also monolithic heat shields like Orion's AVCoat or Apollo's AVCoat. Recently, they're rethinking the Orion heat shield AVCoat TPS material strategy. But the problem with all of those TPS materials, whether they're these ablators or ceramic tiles, is that there's always a tendency for these materials to crack. And so handling the structural implications of the materials is just as important as being able to have those materials work from a thermal protection standpoint. If you have a compliant TPS material, that essentially means it's like cloth. It's flexible. It allows you to mold it into whatever shape you want and allows you to drape it over the heat shield or the structure, the heat shield underlying structure. And by doing that, you then no longer have to worry about cracks. Later on, if the heat shield has to go through different temperature cycles, and so it's going to expand or contract to some extent, a compliant TPS material can handle that. So these TPS materials, woven TPS materials, have all the way down to a fully compliant capability where you don't impregnate it with a resin that will make it more rigid, all the way to a fully dense form that's very similar to carbon phenolic, which is what we end up using for outer planetary missions or missions to Venus, where we have a very dense material. And that ability to adjust that material over that wide range is the TPS material of the future. And so we're working on a range of these materials. Like I said, the first one will be flying on Orion on its next flight and subsequent flights. And then many other variants of that are going to be optimized for the various application missions, whether that means a large mission to the surface of Mars or any other planetary missions where an atmosphere is involved. We're also looking at the fact that Orion will need new capabilities beyond what is originally on board right now. One of these capabilities is heat rejection. If you go to a location like lunar retrograde orbit, which is being examined as the proving ground destination for Orion, it's actually a fairly challenging place in terms of getting rid of heat. So we're looking at two different types of phase change material heat exchangers. These are things that if you use water, you're transitioning from solid to liquid or wax from solid to liquid. And that phase change is actually what you use in order to store and reject heat through that phase change process. So we're developing two of those phase change heat exchangers. We're going to demonstrate them at scale on ISS. And what we think is the most qualified for Orion will eventually be on-ramped and infused onto Orion so it could perform those missions of the future. We're also looking at composite cryogenic propellant tanks. This is a huge way of significantly reducing the mass of the upper stage of SLS if we could get it onto that vehicle. Every pound of the upper stage that you pull off adds to payload mass that you could add on. So if you could reduce the mass, the dry mass of the upper stage by 30%, all of that mass translates directly into payload. That's an enormous benefit in terms of, or leverage in terms of increasing the payload of SLS and, for that matter, any future launch vehicle. Now, in the past, we've tried to do this not just for the dry structures, and on the non-human launch vehicle side, there's a lot of dry structures that are already composite. So this is not new to the launch vehicle industry. It would be new to a human-rated launch vehicle, even for dry structures, and we're working on that today. But beyond that, nobody has ever licked the problem for a large launch vehicle of actually doing cryogenic, and I'm talking about liquid oxygen and even liquid hydrogen propellant tanks, and actually having them as part of their launch vehicle. If we can do that, it makes a huge difference, as I indicated, especially for the upper stage where performance is so translates direct into payload mass benefit. In the project that we just recently completed, we actually demonstrated a 5.5 meter tank that was storing liquid hydrogen, and we put it through all the pressure and load cycles that are necessary for a launch vehicle. Anybody that is familiar with X-33 knows that we tried this before and we failed miserably at being able to use composites in launch vehicles. That was a tougher problem than the one that we took on here, but we do feel like we finally retired the ghosts of X-33 and we're ready to move on and incorporate composites into launch vehicles of all types and eventually get to the point where we're including them into vehicles, upgraded versions of SLS, where those composites will translate directly into payload increase. The next step that we're taking is to say, okay, we now understand how to build all kinds of composites for launch vehicles. Wet structures, dry structures, all of these structures. We actually know how to do it. The technology is now in hand. Certifying these technologies and going through all of the pieces, like how do you attach a new piece of hardware to a composite when the composite is a sandwich? How do you transfer the loads from a composite structure, dry structure or wet, to a metallic structure that you may have to have as part of your secondary structures or as part of a payload shroud or part of some other piece of the overall vehicle? Working through those details, working through the certification, working through what are the safety factors that you need, working through how you examine it to make sure that you don't have a DLAM or other problem. How do you fix it if you do have a problem? Working through all of those issues is actually where we're at today with the technology. This isn't anything new to aviation world. They've actually worked through most of this for commercial aviation with the Boeing 787. However, if you talk to the folks that did that, they actually will tell you that it was a huge jump that they had to take, and it actually cost them significantly in getting that plane to the point where they could fly compared to where they were originally at. We need to go through the same process with launch vehicles today, and we're taking those first steps by including development of composite components specifically for SLS upper stage and going through and learning what is that certification process. Here's another list of technologies that we're working on. These are technologies that we're working on with AES, Advanced Exploration Systems, and SCAN. Again, I'm not going to go through this list. If anybody is interested, please get a hold of me. Happy to talk to you offline. I'll go through a few items here, though. High-performance EVA technologies. We're doing several pieces for EVA suits. These are just a couple of the components. Rapid cycle amine, portable life support system is what it's going to be integrated into, and a variable oxygen regulator. We've delivered this to AES. They've actually integrated into a test bed, and we've gone through multiple cycles of this. We're also looking at technologies that go beyond traditional habitats. Several of the earlier talks have talked about the fact that we need a habitat in space to get us to and from Mars. You can't just ride in Orion itself. We're going to have a habitat attached to it. Well, in addition to that, we also have to have things like airlocks and ways of getting in and out of those habitats. Traditionally, one of the most heavy components of an airlock is actually that hatch. You have to have a metal ring around the hatch, and the hatch itself has to be built out of all metallic components, and those metallics are extremely heavy. So in this effort, we're actually going to try to remove all the metallics from the hatch itself on an airlock and replace them with soft goods, essentially cloth. Now, if we can do that, we're going to drop a lot of the mass, and you're going to be able to store this thing in a much smaller volume when you're taking it to and from orbit. We're also looking at specific technologies for Mars itself on our own. This is STMD, or the Space Technology Mission Directorate, funding these essentially on our own, as opposed to partnered with AES, Scan, or partnered with SLS or Orion. So again, we have another list of technologies. I'm not going to go through them, but I'll cite some examples. Over and over again today, we've heard about solar electric propulsion. I'm not going to kid anybody and say that solar electric propulsion is the answer to fast transit of crew to and from Mars. So if you want to get below 6 months or even 9 months of time, you're not going to get to Mars with people. You're not going to do it with solar electric propulsion. However, everything that you could take to Mars, besides the crew and the accommodations of the crew, such as pre-placing your ISRU plant on Mars, pre-placing the power on Mars, pre-placing the actual propulsion system that's going to take you back to the Earth. All of those items, you could put them out there at Mars using solar electric propulsion at a fraction of the cost that it would cost you to do it chemically. When I think of solar electric propulsion, I think of the same thing as when I think of a car as gas mileage. And I think of the ISP as my equivalent of gas mileage. So if the ISP of a solar electric propulsion system, like we're talking about here, is 3,000 compared to the ISP of the best chemical systems being under 500, you got a factor of 6 improvement in gas mileage. So you have to take 1/6 of the total propellant to get you to Mars if you use solar electric propulsion. So it's a huge driver. Others have talked about the fact that we may need 5 or 6 launches to get to Mars with SLS, and we're talking the big version of SLS. That seems like almost an unaffordable mission if it's just to send a few crew there and bring them back. If we could cut the number of launches that's necessary to get to low Earth orbit and then put everything together for our mission to Mars, we can make it much, much more affordable. That's what solar electric propulsion buys. So we're doing that. We're going to do a demonstration of this at 25 to 50 kilowatts, but this will be fully extensible to the point where we could take this and do 300 kilowatts, and it really becomes the SEP tug that could move things around our solar system. I'll go forward. We're also looking at an ISRU experiment on Mars. This is to convert the Mars CO2 atmosphere to oxygen. If we can do this, we could use it not only for breathable air for the astronauts when they're spending up to a year on the Mars surface, but it also means that we could produce the oxidizer for the Mars ascent vehicle. And that is important because 80% of the liquid or propellant load, including the propellant and the oxidizer, 80% of that, of the ascent vehicle, is actually the oxidizer, the oxygen. So if we could produce that, we could cut the amount of mass that we need to take down to the surface by that huge amount, and then again reduce the number of flights we have to get to Mars. So producing as much as we can from the Mars surface is important. This is the first step. We're going to actually do this on Mars 2020. We're partnered with the Science Mission Directorate and the Human Exploration Mission Directorate to go do this experiment. And the idea is to scale this up to a real plant so that we could actually have oxygen produced on the surface. Oops. Now, in addition to, in order to be able to produce that oxygen, we need electricity on the surface of Mars. There's a lot of different estimates of how much electricity we'll need. We're taking the first steps of looking at very affordable and reliable and maintainable fission reactors as a power source. And so what is different about this fission reactor is it is connected to a Stirling cycle by a solid-state heat pipe. No liquids cycles. In other words, it's all solid state. It's like going from vacuum tubes to integrated circuits. If we could do this, we're going to do it at very low power at first, but if we could pull this off, then we could have cheap, reliable, and easily maintainable fission reactors for space applications, not just for the surface of Mars, but potentially for many other applications. So we're also looking, of course, at how do we make sure that we could do life support systems of the habitats themselves. We're doing Sabatier systems today. They're about 42% efficient. They actually work very well on station for compared to what we originally intended. They were actually a technology and experiment on station that has been moved over to actually an operational system. However, if we want to go to Mars and we want to do it efficiently and we want to again cut that mass to low Earth orbit, we want the most reliability that we can get, and we also want to have it the most efficient in terms of converting CO2 back into oxygen, recovering as much of the oxygen as we can. And so we're investing in technologies that will do 75% or better. In some of the cycles that we're actually doing initial studies on are 100%. They're going to fully recover everything, so there's closed loop. So we're doing the first steps in looking at that today. Obviously, there's a pathway of maturing these technologies that we've all talked about. These are at the benchtop level today. We also need to get down to the surface. A lot of people talked about that. Some of the designs had inflatables, some of them had mechanical deployables. We're looking at multiple concepts, and we're funding the technologies to actually mature those such that they will be ready when we're going to Mars with large payloads. Currently, the limit that we could get on entry is Curiosity, which can, or Mars 2020, which could take 1 metric ton to the surface of Mars as payload. In order to be able to do human missions to Mars, the low-end estimate is we got to be able to put 10 metric tons on a single shot to Mars. The high-end estimate is 40 metric tons. We want to push that as low as we can, because the higher you push that number, the harder the EDL is. And even the entry piece of it is hard. So why do we have these inflatables or mechanical deployables? Well, it's very hard to fit in a launch shroud if the diameter of this inflatable is 20 meters or more. So what we need to do is find a way to be able to essentially pop that aeroshell out, either mechanically or using inflatables. This is where those compliant TPS materials I talked about earlier become very, very important. So we've done demonstrations of HIADs. We've actually done some ArcJet testing for both the HIAD and the ADEPT concept. We're looking at initial demonstrations of those. We'll at some point have to down select between HIAD, ADEPT, and maybe a mid-L over D concept to say what is the actual technology that we're going to use to get to the surface of Mars. And we'll likely have to have a large-scale demonstration of this technology before we're going to put people behind it and say it's ready to go. We're also looking at, if you look at EDL, there's segments of it. Another difficult problem is the supersonic deceleration. All the way from the point that you get rid of your entry system or heat shield down to the point where you're doing terminal descent, there's a segment in which you need to be able to slow down. Everything on Mars that we've sent thus far has used a disc gap band parachute in order to perform this deceleration. We're looking at a range of technologies that will allow us to go to much larger payloads again in order to get to the surface of Mars. We've done successful demonstration of portions of this last summer out of Hawaii using in the LDSD program. Anybody could go online and see a pretty exciting demonstration in which we actually took a 30-meter parachute, much, much bigger than anything that has flown before at supersonic conditions, and shredded it. No surprise. Most people in the parachute industry will tell you that the first time you try any parachute, you're going to shred it. So this is a difficult technology to mature. We've taken the disc gap band parachute technology up to its limits. We're not going to get above 1 metric ton to the surface of Mars unless we go to these other technologies. And that's why we're actually flying them in a Mars-relevant environment. We built a special, not an aircraft, but a rocket-powered spacecraft that flies at 200,000 feet in the Earth's atmosphere in order to be able to test these devices at supersonic conditions, which is equivalent to the same dynamic pressure and Mach number that they would see at Mars. Oops. So one last thing. We also are working on deep space optical comm. We're doing this in partnership with the Science Mission Directorate, and we're doing it in partnership with Human Exploration. And in the case of the Science Mission Directorate, we're actually trying to infuse this technology on the next Discover mission, where we will demonstrate this. If we can do it, you can, for the same power and mass budget, you could do 10 times the communication bandwidth fairly easily using deep space optical comm. You could do it the other way around. You could say, well, I want to instead of you could keep the same bandwidth, and you could say, I'm going to reduce the mass that's required by a significant amount, or reduce the power that's required. It's pretty well given that if we're going to go to Mars with people, we better have some high bandwidth return. I don't think people are going to be happy on Earth if they don't have anything but an audio link coming back from Mars. There's no high-def video that's running all the time that's coming back, even though it's 8 minutes delay. If we don't have that kind of a bandwidth return, I don't think the public appreciation for the program is going to be anywhere near as what it needs to be. And so we got to work on all of these pieces, and that's what the Space Technology Mission is all about. So I'll end with saying that we think that technology drives the exploration. Without these technologies, we really aren't going to get there anytime soon. And I don't know if I have time for questions or not. How did I do on time? Nope? Okay. Buzz, you got the one question.
Can you hear me? Can a well-designed Mars lander for the terminal descent be used as a lunar lander? With what kind of modification?
So I'm going to dodge that question in a way. So if you are using supersonic retropropulsion as part of your descent system, then you're not going to have a different set of rockets do the terminal descent. You're probably going to end up using the same rockets that you use for your supersonic descent, and you're going to have to make sure that those are capable of throttling down to a very low level to be able to handle the whole spectrum. That system is probably going to be way overkill for anything like a lunar application. If, on the other hand, you were doing maybe just aerodynamic deceleration for Mars, and you only needed the terminal descent system to be a much smaller propulsion system, there might be some commonality. But I would say that the lander itself would be a different beast. You might be able to leverage some of those propulsion technologies.
You got too much propulsion?
It's a lot harder to do the deceleration at Mars through supersonics all the way down
But you
than.
don't have an atmosphere at the
That's true, but that's helping you most during the entry phase. It's not helping you so much during the supersonic descent, and it's not helping you so much at the terminal descent. Gravity is a much bigger player there.